Hello everyone, David Ostrowski, and this is week 11, MCS 2534. In this recording, I'm going to be giving an overview and take a look at some of the related concepts and algorithms around working with graphs. So let's get started. We'll look at the basic structure of a graph. Okay, it consists of vertex and edges. So the vertex is every node on a graph, and the edge, identified by E, are the associated connections between those nodes, right? So vertex is identified by V, edge is an E, and that's the basic starting point for looking at a graph as an abstract definition. So a couple different representations of graphs. You can have an adjacency list, and this is going to be pairwise combinations. For example, a vertex would consist of, an edge rather, would consist of the two individual vertexes identified as pairs. So this is best suited for graphs that are not completely connected, or even in representations or applications of algorithms that perhaps it's a little bit best suited in terms of efficiency, because compared to, let's say, a fully connected graph, you wouldn't have that much information to store it, so it'd be stored as very small. We'll see that as we get into more implementations. With an adjacency matrix, you have all of the vertices on kind of an XY axis, and you can represent it as a Boolean type structure, right? That either they're connected or not connected. So you could set it up as a 1 or 0, or you could have alternative representations, but it would basically boil down to the same type of representation. And we could even break it down. I could pull in Notepad here and just kind of rough it out how it looks even before we get into the details. So here, if I looked at this first undirected graph, and what we mean by undirected is there's no direction, so we're not putting in excessive direction, where this is compared to a directed graph where you wouldn't be able to go from, let's say, 1 to 2 if you had an arrow pointing from 1 to 2, unless you had an arrow pointing from both angles. But again, more about that as we go on. So if I would represent this as a adjacency list, I might use the following format, and I'm not limited to it, right? You could use a JSON-based format, but here I could say pair 1 to 2, right? And I would also have 1 to 5, and then I would have 2 to 5. And if it's undirected, if it is directed, then I might be inclined to have a 1 to 2 and not a 2 to 1. Okay, but you might imply, and again, there's some alternative forms of representation here, but 2 to 5, let's do all the 2s, 2 to 4, and 2 to 3. And I could say 5 to 2, 5 to 4, but 5 to 1, but that could be implied here. So just for simplicity, I'm going to put 5 to 4 because that wasn't represented prior to this. So that includes all the connections with 5, all the connections with 2. If I look at it from 4, I could go 4 to 5, but if it's not, if it's not applied, right? So, but I need to have a 4 to 3, and I already have 2 to 4. You could argue that, or have a means of representing. Hey, I could represent that as a 4 to 3 and a 3 to 4. Okay, but if I just say, hey, it's undirected, I have those pairs, then it could be implied, right? So unless I have more of a strict definition. So this would be, as you see here, adjacency list. And if I look at it as a matrix, I would have it a little bit harder for me to represent in this way. I could say I'm going from 1 through 5, so I'm going to tab through 3, 4, 5, and down here 2, 3, 4, 5, right? And whoops, that would be appropriate. So let me space this over here. So this would be more represented. So I would have a matrix, and in this case, I would go through for the top graph. I don't have to identify 1 to 1, so it's 1 to 2. So 1 to 1, I could put in a 1 or 0, really wouldn't matter too much. And then I could say 2 to 1 is a 1, and the rest are zeros in this case. Here I would have 1 for the 1 to 5. So forth, and 5 to 1 correspondingly, right? So and I just continue on. So 1 to 2, 2 to 1. Okay, I can say indicating again this is undirected. If it was directed, then I would have perhaps one of these is 0, one is a 1. Okay, if I'm only looking at a specific direction, you can think of a pathfinding application here, right? So now it's well beyond pathfinding, right? I can use graph representations among a number of different areas. So 2 is 2, right? I could set it, I could argue either representation. 2 goes to 3, and 2 goes to 4, and 2 goes to 5. So I set that up as 1. I'm sorry, this should be a 1 here, not a 5. Okay. So you can see where I'm going with this, right? You should be able to anticipate how this representation work as an adjacency per the term, right? We're saying what in logically speaking, a 1 is adjacent to a 1, right? Or the 1 is 1. But, if I see 3 to 1, that would does not exist, so I put a 0. 3 to 2, that would be a 1. 3 to 3, 3 to 4 is a 1. And 3 doesn't go to 5, so that would be set up as such. 4 would be connected to 5, 2, and 3. So everything else would be a 0. Whoops. And this looks a little bit, makes a little bit more sense if it's a little more symmetrical as a matrix, but we'll do the best we can here. So 1 and 5 and 4, right? So 5 and 4 are 4 and 5, 2 and 3, and not 1. Right. Then the last one would be 5 to 1, 5 to 2, not to 3, and 4 and 5. we go. So there's the an example. Again, we can work through more examples here. Both have their strengths. Again, for large graphs, the adjacency list may make more sense. In either case, it's really not that inefficient to start, right? So you get your idea where we're going with this, right? GraphSearch, okay, you can do breadth first or depth first search. Now, depth first search might be related topological sort or strongly connected components. The main point between graphical search, right, is the fact that it is important to look at what we've studied with searching a tree and a graph, and appreciate that the fact that a tree, when you think about it, it is a restricted graph. Okay, it is and a binary tree is even more restricted. So finding the similarities, and this goes back to some original points here in the class, is that it's important to understand and appreciate, which hopefully you do at this point even, of the fact of looking at these data structures as abstract data types, because it finds more commonality and common relationships. And when we have that, we have this classification. The whole idea is to share among the community. And as we get into deeper issues around the NP complete, this speaks to the fact, right, that if I have a categorization of a problem, and if I can relate one problem to another, problem reduction, okay, this allows me to take solutions and apply them to greater utility. So if I categorize a problem as a depth first search, and let's say I define a better way of solving that type of problem, and maybe it's for a completely different problem, right? Different application. As long as you're categorized in the same fashion as on an abstract level, you're just that much better. It's going to be applied across the board. So that speaks to the fact of the value. Okay, and that's the bigger picture, right? To appreciate in both the concept of abstract data type and problem reduction and categorization of problems, and the whole idea around algorithm analysis, right? So all these concepts tie to one main theme that is threaded throughout all this, is commonality of solutions, a categorization of problems, and community. And what I mean by community is borrowing from the research community, which again I'll speak to more detail as we get into NP complete and some of the more related topics. Representation of graphs. Okay, adjacency list. Okay, and that's omega v plus e. Okay, preferred for a sparse graph. And in this case, the adjacency contains all the vertices v such as there's an edge u to v within e. Okay, so this is where we're taking consideration of the edge and we're associating weights to them. This is, again, speaks to my earlier points that not all problems have equal weight to a given path. And perhaps the most practical application of this might be even, Google Maps or some type of um, geographical um, pathfinding, right? That not every path is optimal, and this distance is not necessarily the optimal weight, right? You could have other factors. You could have traffic, you have streetlights, you could have speed limits. In cases of less urban type of paths, it may exist as physical obstacles that exist in urban as well, right? So this speaks to a lot of points that assigning the weights are really important here. What are we interested in? Again, what's the big theme for all of this is finding the right solution for a given problem, and this speaks towards efficiency, right? And it's not just a factor of, well, if I can traverse less nodes, then I have a better path. That may not necessarily be true. And a classic example might be road construction or something of that nature. So if you have an alternative path, it may be optimal. Going back to Google Maps as our example, right? You may have paths for taking public transport, for personal transport, or even walking, right? You may have seen, if you have paths that are suggested for given solutions. It can be through different means, and these would all have unique weights assigned to that. So something to keep in mind and I bring this up immediately, right? Because it speaks to the fact that the more that I can draw the real world associations to this, right? Then everything that we're doing in terms of an abstraction, right, is going to speak to the novelty of these solutions, right? Moving forward, the adjacency matrix, okay, omega v squared. So this is preferred for a dense graph, and there's a symmetry for undirected graph. Here, the weighted graph. You store the weight of u to v and the uv entry, and easy determinant of a given edge is represented in the graph. When I go through these, okay, another thing that comes to mind is the directed versus undirected graph, because obviously if you have a directed graph, you can have weights associated to one direction and unique weights assigned to the alternate direction. So this speaks again to the nature of directed graphs and exactly how important and relevant they would be to a given solution. So more about this as we move forward. So here's a physical represent. Again, we can do a lot more representations. They have here's a representation for undirected graph, and I use the pairwise combination. Could be likened to a key value, which almost a JSON-based representation of what I had in mind would be. But here they presented almost a linked list or a list of lists or an array of lists. Any number of ways you can describe it. It doesn't really matter, right, how we physically implement it. It is more about how it is specifically represented as an abstract data type, right? And then you saw here with the adjacency matrix, and so interestingly, the self, the node, they identified them all as zeros, and this speaks to, they did a little more cleaner than they did in Notepad, because I can't really do the columns and rows as in the symmetrical matrix representation, but you can see how that shows up here. And again, for undirected graph, right? 3 goes to 2 and 2 goes to 3. You could even, for an undirected graph, speaking towards larger efficiency, I could look at any side of it's a mirror image, right? Both sides of the left-right diagonal. So I could actually use half of the Boolean bits to represent that if that's important. Okay, in a given, maybe in some cases it isn't, and in all cases it doesn't have a lot of it's not a big difference, okay, in any case, okay, unless it gets really, really big, and it can be substantial. Now we're looking at a directed graph, and this speaks towards the differences, and you can see here it is not symmetric, right? It's not symmetrical on either side of the diagonal or mirror image. So let's go through that here, and I can pull my little notepad here, and we can play around with that. You should just have, if you haven't had any prior exposure, it can help, okay, to just see if you can write that yourself. And again, this is a great starting point, right? If I wanted to look at a directed graph in the way that they're representing it. And I could do the pairwise combination here. They just add it as a linked list instead of saying 1 to 2, 1 to 4, the same thing, right? So if I go with my alternative representation, whoops, that would almost imply that I had an issue with the thought I lost my audio there. Might have lost it. So that would imply that I would have more restricted graph. Okay, when I'm using the tree here. So next, I would have first out Q. I defines Q to manage the set of gray vertices where Q stores all the gray vertices. So here we go in graph, and we can identify depth for search appropriately, right? So here I'm starting at the A position with S0, and we're looking at weights. We're looking at an equally weighted graph, right? And we're going to say, well, if I'm going to do a depth first search, so I can think in terms of pathfinding if I really want to go a few steps forward. It's not necessary, but it can give you a little bit more idea of, again, how it could be accomplished. So I go from 0, and then Q is established as going to from S to R, T, and X. But what I'm doing here is I'm moving from S to W. Okay. So I move from S to W. And the gray is indicating all of the adjacent nodes. Okay. Why am I saying that? Because at the end of the day, I may fall into a position, if I'm looking at a weighted graph, that the next least weighted graph might be, or means of exploration, might be going to R. Okay, so that's where I'm saying, hey, as I expand my path, if I'm searching for a solution, I am going to consider all possible nodes that could be accessed. So here I have R, T, and X. And that is associated with Q because I already know that in my solution set I have 0 and 1. So from there, whoops, I'm sorry, I went from A to B. I skipped to C. Sorry about that. So I go from 0 to 1 and 1. Those are my possibilities, right? And I weight the solution appropriately. And here I'm assuming an equal weight. So I make the transition to R, and I make the position to T. They're both weighted as a 1, and that's indicated up here, okay? So I have that. If I'm going to expand beyond that, then I'm going to say, well, I got R to consider. I also have F and X. And that's among my possibilities that I would consider, okay? and I'm sorry, that's a T. Let me get my glass on. Sorry about the presentation here. So I go to, it's from S and W. I have R, T, and X. And R is 1 from the starting point. But T is 2, equal weight of the vertices, the edges, and so is X. So that's among my choice. So the shortest path to extend is, in this case, would be R, because it's only 1 vertice. And why do I do that? Is because if I have a given solution that I'm going to, I want to look at all the possible solutions, I may be 1 node away from a given solution. But I don't know until I reach that point, right? So here I pick R, and now blackened I have S to R and W. If you notice, he's been changing from infinity, and we set infinity just the highest possible number because we don't know the complete cost of getting to that location. So I go S to R, excuse me. I have everything from S, R, and W. So that includes T, X, and V. And these are all weighted equally. So that, given that, they make the choice of going to adding T as the next possible search. And here's the quality of the breadth first, right? Is that anytime I make a choice for additional node, assuming that they're not the same, the choice is only among the grade areas. Here, my 2 grade areas were the 2 adjacent nodes. Here, I had the 3 adjacent nodes to the 2 that I selected. Here, I had the 3 additional adjacent nodes relative to the 3, and then so forth. I have 3 more with the 4 nodes that were chosen among all my possible paths. Here we're just doing a complete evaluation of the graph structure, right, from a breadth first type of evaluation. And with the E, I have X, V, and U, 2, 2, and 3. Why? Because it would take me 3 edges to get to U, and 2 edges to get to 2X or V, right? And that's why the X is 2, V is 2, U is 3. So I would pick the X here as the next one because it's first in the queue. And then I would have the remaining 3, they're all evaluated the same. And in that case, they picked the V, which I believe was the first one, right? It would be the first, it was evaluated back in D. So I kind of look at it from a first means evaluation, right? Depending on how I'm doing the traversal. And then I have U and V are 3 equally. Then I would go to U and 3. I could look at this as the first out Q 3, and now I have everything, all my weights associated from point S. And again, this is given equal weight. I may not have equal weight, but again, it gives me means of comparison. It gives me a first-hand evaluation, right, of the use of depth first. Here's another example of depth first. I have A to go to B, and And here, they don't step you through all the way. Let's see if we can break that down a little bit. And here we have, interestingly, directed graph is not undirected. So we can look at only at specific adjacent nodes. We can't go from A to E. We can only go from E to A. So I go from A to B, and then from B either to C or F. And considering from C would be to D or G, and B would go to C to F, and so forth. So it'll follow in a similar fashion, right? Let's see if we can break that down. Here's the algorithm. Okay, so we've kind of seen the mechanics of that, and hopefully from that we can make these transitions and see exactly how they would be represented as a breadth first search from an algorithm standpoint, right? So this kind of speaks to what we did, but kind of put it into more algorithm perspective. And you can, again, you could assign this to any language. So you say for each vertex U, the V of G, you'd obtain S and do the color, is assign it to white, and assign out the vertex to infinity and the pi of that position of nil, and set it to gray, 0, nil, and I would do the NQ. And while the Q is not equal to the null set, I do the DQ, and for each adjacent, if it's white, then I color it to gray and put in the NQ appropriately. And again, we'll break this down a little bit more as we go through this. So let's look at the analysis of the breadth first search. Here, the big O of V plus C, each vertex is NQ'd. It's big O1 at most, okay, and each adjacent list is scanned at most once, big OE. And I can print out the vertices on the shortest path from S to V, and I can use a print path, V is equal to S. And print S, if pi V is equal to nil, then print no path exists. Otherwise, print the given path, right? So here's an illustration of how it would be printing out the path, and I kind of print it out as more of an adjacency list representation. If I'm going from S to Y, and I can say S to X, S to W, S to S. And here, again, I can see the associated paths that are taken, and I'm assuming that I have bidirectional. W, X, Y, S, W, X, Y, right? So you can see how they would be applied and be able to generate the associated paths. So let's draw a means of comparison between this and the depth first search, the DFS. So DFS, we search deeper in the graph where it's possible the edges are explored out of the most recently discovered vertex V. It still has unexplored edges leaving it. When all of V's edges have been explored to finish, the search backtracks to explore edges leaving the vertex from which V was discovered. This continues until we have discovered all the vertices that are reachable from the original source vertex. If any undiscovered vertices remain, then one of them is selected as a new source, and the search is repeated from that source. Here, the entire process is repeated until all vertices are discovered, and DFS will create a forest of DFS trees. So the data structure of DFS, they rely on an adjacency matrix. You have a color of U for each vertex. Again, in similar fashion, white if it's not been discovered, gray if it is discovered but not finished, black if the U is finished. And the timestamps exist, okay, from 1 to 2 to the vertices. The DU of the records records when U was first discovered in grade, and the FU requires F of U when the search finishes examining the U's adjacency list and blackens it out. Here you have the pi view for the predecessor view. And here is how it would be applied among a directed graph, right? So I had to start off with U, logical starting point, because it's an originator node. So, and I'm assuming equally weighted path, right? So here, first step is to look at, to gray out the area breadth first. So I go to U to V, as you see in position B, or depth first, not breadth first, right? So I take the depth and I go all the way as far as I can go, right? Until I can't go any further, right? So that's why I don't make the decision, because for the associated path, because I don't stop until, and this is in comparison to the breadth first, right? Where you look at all adjacent nodes. Here I take each node as far as it can go, okay? Or you can't take it any further. So I would go from U to V, gray that out, and I ask the question for V, where can I go? I can only go to Y. And from Y, the same question, I go to X. Now from X, only make a cycle, so I know that that is as far as I can go, right? So in that case, it gets blacked out. And now I can proceed, right? So from the X node, I can go to V, and I'll take that as far as I can go, right? I go V to Y, and in that case, I would darken out the V and Y path, right, associated, and I have that bring us down to I here. Now again, I see how I can move forward here. I can go from X also to, from V to U. Okay, so that was a secondary path, and that would be darkened out as well. So I've exhausted everything. I set up my paths. Here I would look among kind of, I've exhausted the depth. I go back to the next adjacent node, or in this case, originator node, which would be W, right? And W, gray that out, and that would take me to Z, darken that out, and then I would darken out Z as accept the path, and finally W, and have all the associated nodes are brought together, okay? So the depth first search, again, I think it speaks well to the need of being able to visualize and kind of follow through the mechanics of the algorithm. Then when you look at the actual written algorithm, it should make sense, right? And we can go through more examples. I think this is a good starting point. But you want to relate what we're following through graphically with the generic algorithm that's being presented here, right? So depth first search for G for each vertex. In the view G, do the color to white. Let's set it to no for the pi. For each vertex, if it's white, then I perform the depth first visit, which is the subroutine here, identified just below. I set it to gray and increment my time. And again, we have directed edges. However, they are not. They don't have unique weights assigned to them. Okay, so for each V in the adjacency of U, explore that edge with the colors white, and then set it to the pi representation and do recursive call on that visit. It is interesting to note, right, that both of these can lend themselves to recursive implementation. It's not absolutely necessary, but you can apply it in that fashion, right? So, so it's the time complexity. Okay, it's omega v plus c, and the visit is called exactly once for each vertex. Loops on lines 4, 7 for vertex v. The total time is adjacency v to the I'm sorry, I think it's omega v, not the theta, right? So DFS results in the forest of trees. Discovered finishing times have a parentheses structure. So here we have analysis of some of the representations here. And let me see if this goes back to the last. So here I have X and is spread across this representation, and you go into Z because that's the only path, right, that's involved. And from Z, you're going to Y or potentially W, okay? And then from Y, you have X, right? So you're always going to go X, Z, Y, X, right? And that's the depth first. And this is putting it, this is giving you really more of a tree-based representation. And here you can see the with the bottom representation is giving you more of a tree, right? So this is kind of giving you a little bit more insight of the relatability that I spoke towards earlier, that I can take the graph, and if I add a little bit more structure, I can put it closer into a tree-based representation. The more I can do, the better off I'm going to be. Okay, it's as simple as that, because I want to make that direct association. Let's look at the classification of edges. So tree edges are edges in the depth first forest. Here the edge UV is a tree edge. It was first discovered by exploring edge U of V. V is white. Back edges are those edges connecting a graph, connecting the vertex rather to an ancestor V in a DF first tree. So kind of drawing the relationship, okay, between parent and ancestor, okay. And we're using a more generic term here because we don't have as strict of a format, right? So in this case, the soft loops which may occur in directed graphs are considered to be back edges. The V is gray. The forward edges are those non-tree edges, U of V, containing the vertex to a descendant V in depth first search tree. the V is black and the D of U is less than the D of V. Cross edges are all the other edges that can go between the vertices of the same tree as long as one vertex is not an ancestor of the other, or they can go between vertices and different diverse trees, okay, where V is black and perhaps D of U is greater than the D of V. In a depth first search of an undirected graph, each edge of G is either a tree or a back edge. Topological sort. The directed cyclic graph is a linear order of all its vertices, such as that if G contains an edge, U of V, then U appears before V in the ordering. If the graph is not a cyclic, then no linear ordering is possible. Topological sort can be viewed as an ordering of its vertices along a horizontal line, so that all directed edges go from left to right. Here, the DAG is used in many applications and indicate precedence among events. And I think, again, the more closer approximation that we draw this between a tree-based representation of graph, remembering that a tree is a graph, it's just more restricted, right? But if we can draw those associations, this helps with our understandability. When you look at a tree, you immediately can see and appreciate the difference between breadth and depth first search, because you're physically moving from the top to the bottom. Here on the bottom, representation is not as immediately apparent, so that's important to understand and appreciate that. Topological sort, so you call it depth first search, to compute finishing times of f of v for each vertex v. As long as the vertex is finished, you insert it in the front of the linked list and return the linked list of vertices. So cyclic graph, this is the case where a depth first search of G yields no back edges. Suppose there could be a back edge, U of V, if the vertex V is an ancestor of vertex U in a depth first force. Then there's a path from V to U in G and back edge U to V. And in turn, this would complete a cycle. So suppose that G contains a cycle C. We could show that depth first search of G yields a back edge. Here we let V be the first vertex to be discovered in C and let U of V be the preceding edge. At time D of V, the vertices of C form a path from the white vertices from V to U. By the white path theorem, vertex U becomes a descendant of V in the depth first search. Therefore, the U of V would be viewed as a back edge. So we look at topological sort. Okay, this is going to produce sort of a directed cyclic graph. Here we suppose that depth first search is run on a given DAG, directed cyclic graph G. To determine finishing times for vertices, it suffices to show that for any paired distinct vertices V and U, there's an edge from G in G from U to V, where f of V is less than or equal to f of U. Here, the linear ordering is corresponding to finishing time ordering. And here you consider any edge U of V be explored by the depth first search. When this edge is explored, the V cannot be gray, otherwise U of V would be a back edge. So V would either be black or white. So if the V is white, it becomes a descendant of U. Where the f of V is less than U. If it's black, it has already been finished, then f of V has already been set. So I hope this helps. Any questions, let me know. And I'll see you on the next recording. Okay, take care. Talk to you soon. Okay, bye now.